see the title Edge Cloud and the Smart Building. Please welcome Melanie.
Can everyone hear me, or do I need the microphone? The microphone, right?
Yes.
Okay, so very warm welcome from my side as well. Thank you for the introduction. As mentioned, the official title of this talk is the Edge Cloud and the Smart Building, Smart Grid Continuum. And to be more precise, what this talk is going to be about is how we can integrate smart buildings into the smart grid at the energy edge. And when I talk about the energy edge, I mean that we will not be looking at the big players like the commercial producers and the industrial plants, but we will really look at how we can integrate individual households, like your household, my household, and enable them to kind of make the grid more stable, more reliable. Now, the work that I'm going to present is actually what we're doing in the project, in the EU-funded project Bluebird at the moment. And yeah, I don't want to talk too much about this now. We will have a very detailed look at it right now. But the first question is, why do we even need a EU-funded project for such a topic? And when we look at how the energy market was back in the days, basically most or even all of the energy was produced with fossil fuels or nuclear power. And that made it pretty easy to balance supply and demand because we could just produce whatever energy was needed at the moment. So when we need more energy, we produce more energy. When we need less energy, we just throttle the energy production. So we kind of always adapt the supply curve to the demand curve. But then people realized there was climate change and we had to change something. And obviously fossil fuels weren't that great for the climate. Also nuclear power plants are not really good for the environment, so we needed a different solution. And the one thing that everyone came up with was renewable energy generation, which of course is great for the climate, for the environment, but it makes it a bit more difficult to just balance supply and demand. And one other complication was that at first we had just big production plants like the photovoltaic plants and the windmills, but then also the individual people, like households, started to have their PV plants on the rooftop or maybe on the balcony. So we now did not have the centralized production anymore, but we really had a supply that was much more distributed, it was more and much less predictable. But at the same time, the grid operators still had to somehow manage this balancing of supply and demand. And we already determined supply was not really controllable anymore, so the only option that we now have is to somehow make the demand more flexible, so that now we don't really adapt the supply curve to the demand curve, but actually the other way around, we try at least to adapt the demand now to the supply curve. And we have different options how the grid operators can achieve this. The one that probably everyone knows is implicit demand response, which means that we have variable prices throughout the day. So the most dynamic program here is real-time pricing, where we really have an hourly varying price. We can also have things like peak pricing, which means we have basically two different prices, and we have a higher price for peak hours, and we have a lower energy price for off-peak hours. And one other program that I wanted to mention here is the extreme day or critical peak pricing, which is that the grid operator anticipates that there will be an event where we have a very high energy demand, so for example a festival or something like that, and then a very high energy price during this event so that the other consumers are incentivized to just consume less energy in such an event. Then there is another thing called explicit demand response, which is incentive-based. And that means that we don't really have these variable prices, but instead the grid operator forms a contract with the energy consumers upfront. And then in this contract they specify that if the grid is in trouble, then the consumers will either reduce their energy consumption or they will even feed back energy to the grid. So when we feed back energy to the grid, that's usually called ancillary services. When we just reduce the consumption, those are typically called curtailment programs. One other program that I want to mention here is demand bidding. That means that the consumers place a bid in the market in which they say, if the energy price is like that, then I will reduce my consumption by X amount. And then when the bid is accepted, they actually have to deliver. And this is of course the same with all these programs. If you are called upon delivering what you promised in the contract, then you have to do this. If you don't, then you get a fine, which is usually very high, so this is definitely something you want to avoid. Now the question still is, how do we actually get enough flexibility that we are able to participate in such programs? And when we look at the sectors that produce the most energy, at the top we have the transport sector, but I mean, if we're being honest, we don't really have much flexibility here, because if you have to go somewhere, you want to go now. If you have a lecture in the morning, you don't want to go in 2 hours, you probably have to give the lecture now, and you don't want to have your students do it. So the next sector that we have is buildings, and actually buildings account for 30% of total energy consumption, and 75% of buildings are energy inefficient. So, I mean, if we look at these numbers, that kind of suggests that we do have some options here, there is potential, but still we need to find the flexibility in these buildings. And this is what I want to talk about on the next slide here. So what are actually flexibility levers that we have inside a building? The first lever is technical flexibility, and one very powerful thing that we can do in a building is to just shift the consumption in time. That means that we consume energy when the prices are low, and then we can reduce our consumption when prices are high again. One very easy thing how we can do this is if you think about your washing machine, for example. Many of them are programmable now, so you can just program the washing machine to start whenever the prices are low. The other thing is, of course, energy storage. So if you have a battery inside a building, you can just charge the battery when energy prices are low, and then you can draw the energy from the battery instead of from the grid when energy prices are high. Then the other technical flexibility that we have in buildings is sometimes we have multiple energy carriers. So you might be able to heat your apartment with gas or with electricity. And if you are able to do this, then you can switch between those two energy carriers, and just when electricity from the grid is not really available, then you can heat your room with gas. Now the other big lever that we have is social flexibility, and this basically means that you kind of have to stretch your comfort zones. So if we think about temperatures, it's really hot right now in Crete, so of course we all enjoy the air conditioning, but maybe if we get ourselves a cool drink from the fridge, then it's also okay to accept like 28 degrees and not use the AC, or at least not power it as much. Same goes in winter, of course, if it's really cold. Of course, we like the 22 degrees in our room, but if we get a blanket and a water bottle, then maybe it's okay to have like 19 or even 18 degrees. Or when we think about the electric vehicles, of course, everyone likes to have it fully charged at 100%, but if we know that today we are only going to the supermarket, then maybe it's also okay to have just 80% or maybe 60%. So even if there's maybe a construction site, you didn't anticipate you have to do a detour, then 80% is probably still going to be enough. But of course, you have to stretch your comfort zones. Now, the main issue with this is still that if you want to participate in one of these explicit demand programs where you form a contract, you need volume. So as an individual household, you are usually not allowed to participate in these programs. And that is actually where our Google project comes into place. Because here the idea is that we pool the flexibility from multiple buildings, and then we have really enough volume to trade this flexibility in energy markets. And here I just want to give you some numbers. As I mentioned, the project is funded by the European Union under the Horizon Europe Innovation Action under Climate, Energy and Mobility. And we have 15 partners from multiple European countries, from both industry and research. And because we are so multidisciplinary and international, we are really able to create a product and then also apply it to use cases. We have demonstrator sites. We can test it with real residents and see how well the solution works. And then hopefully we will come up with a product that can then be also used by other people at other sites. And that means that it actually has a chance to survive beyond the duration of this project. Okay, now to give you like a general overview of the project. The real challenge that we have here is that every building is of course different. So the technology especially that we have in the buildings is very different depending on the house. And also the external circumstances like the energy markets that we have, the legal regulations that we have, they are different in each region, in each country. And that means that we need some solution that can adapt to very different situations and contexts. And the blueprint solution, how we want to achieve this, is by kind of designing a toolkit of digital twins which represent the individual technical components of the building. And then we can assemble these components for each use case, customize them, and then have something that really caters to the demands of each specific use case. Now the components that we identified that have the biggest potential for flexibility are storage, of course. I mean, if you have a battery, that's great, a lot of flexibility. Electric vehicles, they draw a lot of energy, so this is also a really important technical component. Then obviously local energy generation, most of the time this will be PV plants, but I guess in the more northern countries we also might have windmills in the garden or balcony. But in our demonstrator sites we only have photovoltaic plants. And then the last big one is HVAC, so this is heating, ventilation and air conditioning, which just really draws a lot of energy and has a lot of flexibility potential. We could of course also think about lighting and just normal small technical appliances, but these just don't really have much volume, so both in this talk and also in the project we focus on these 4 components. And then at the core of our solution we have a hierarchical predictive control software which consists of these 2 layers. We have at the top the trigger manager which interacts with the market, and then below we have another component which we call the flexibility manager, which basically just collects the flexibility from one building, and then it comes up with a schedule of the ideal energy consumption patterns for this building. So the schedule will determine at what point in time we consume how much energy. But of course, to find a schedule that the users will actually accept and will be happy with, we also have to take into account their preferences. And to do this, we will design an application, smartphone application. And in this application, the users have 2 options. Option number 1, they just specify upfront what their preference ranges are. So if we are talking about temperature, they can say, I like room temperature between 18 and 23 degrees Celsius. That's the first option. Then the second option is that once we have created a schedule and we have implemented it, then the users can still give us feedback on how much they like the current setting. And if they don't like the setting, we would consider this feedback in the next round of generating such a consumption schedule. One difficulty that we encountered was that, of course, we have to do those schedules always for a time that lies in the future. And this means that everything that we do here relies on forecasts and predictions. And because we rely on these predictions, we also have to take into account external events like weather forecasts, traffic, predictions, etc. Because if we think about the traffic, of course, this will affect the commute schedules of the user and therefore the times when the residents are actually in the building. So this is one complication. We are still working on finding out which events and context information are actually important, but this is also one of the big outputs that we expect from the project. Okay, and then once we have the schedule, the trading manager checks the conditions of different players in the energy markets, and then it selects the most lucrative programs to make the most money out of this flexibility that we encountered in the buildings. In the remainder of this talk, I will now go into more detail about each of these components, so about the trading manager, the flexibility manager, and the digital twin modules. And we will start with the trading manager. So the first task of the trading manager is to bid or place the bid in the upstream energy markets, and the concept of what is actually a relevant market really always depends on the regional, on the local conditions. So what markets do we actually have? What technology do we have in the buildings? So if we only have electricity, we of course can only participate in electricity demand response programs. Yeah. And then it forms these contracts. Once the contracts are formed, they are fixed, and we actually have to deliver the flexibility that was promised in the contracts. And this leads us to the next task of the trading manager, because in some way we have to get the buildings to actually deliver this flexibility. And our solution, how we want to achieve this, is by setting internal price profiles. So these profiles specify how much the energy will cost for this building for each time interval. We determine the optimal prices by minimizing the total energy cost from buying minus selling and from penalties from deviating from contracts. This part is really important because, we will come back to this one later, but we really always have to take into account the penalties that we will receive if we don't deliver our flexibility. Then this price profile is sent to the individual buildings, and here the flexibility manager comes into play. So this is the first component that actually receives these price profiles from the trading manager. And it's important to say that each building has its own flexibility manager. In the remainder, we will just look at one exemplary flexibility manager for one individual building. Now, the first task, I think I mentioned this before, of the flexibility manager is to just collect the different options of flexibility in the building and then kind of represent them in a model. We use a hierarchical model here in which we represent the flexibilities, the constraints, and the preferences of the building. And this model is then sent upwards to the trading manager, and by having this model, the trading manager is now able to kind of measure up how much energy it can even trade in these markets. So if you thought that maybe this initial forecast is quite random, no, it's not, because the trading manager does have some idea of how much flexibility the buildings will actually have. Okay, and now we kind of in some way want to exploit these flexibilities, and to do this we use an optimization algorithm, and this optimization is then done at the digital twin modules. So each digital twin module does an individual optimization for the component, for the technical component that it represents. And they will then come up with a schedule in which they say that if the price is as you told me, then I will consume that much energy in each time interval. This power consumption profile is then sent back to the flexibility manager. The flexibility manager aggregates all the intended consumption volumes of the digital twins, and then it sends it back to the trading manager. Now, depending on the technology that we have in a building, we may either be able to feed back energy to the grid or to just consume energy. So we have a negative and a positive balance. The probably most powerful lever here is if we have some sort of storage, usually that's a battery or a warm water tank, because here we can just recharge the battery or heat the water tank whenever energy prices are low, and then we can feed from the stored energy when prices are high, or even feed back into the grid. Then electric vehicles are super interesting because if we have a two-way charging station, then the vehicle can actually act pretty much like a battery. We can just draw energy from the grid and charge the battery when prices are low. But then we can also draw the energy from the battery of the vehicle and add into the grid when the grid needs more energy. So this is super interesting, but of course we also have some constraints. We can't just always deplete the car's battery because the user may want to go somewhere. So here again, the user is a really important constraint. Then the other thing is renewable energy generators. They are always an energy consumer. And the HVAC system is of course always an energy consumer. We just need power to keep the room at our desired temperature. Okay, now the optimization of these consumption schedules is quite simple if we look at storage or electric vehicles. But when we look at HVAC systems, it becomes a bit more complicated. And the reason is that we have an effect which is called thermal inertia. That basically means that even after powering off the HVAC system, we still have pretty much the same temperature for some time because the temperature is just accumulated and stored in the air, in the wall, in the floor, so in the building envelope. And we can now make use of this effect to get flexibility, to really shift our energy consumption, because we can just heat up the room a bit more, cool it down a bit more beforehand, and then we don't have to draw that much energy from the grid when energy is not very available. But of course it also makes the production of these consumption schedule much more complex. And this is why the digital twin modules here need some component of smartness to them to get actually good predictions. Yeah. So here we have this digital twin of an HVAC system, and the solution that we want to implement in the Bluebird project is a model predictive control equation, which has the objective to minimize total energy costs based on the received price profile and on internal costs. So internal costs are important because these are things like the depletion of energy or abrasion or also user discomfort. So these have also to be taken into account. Now the one thing that we can control in the equation are always set points. So if we're talking about temperature, it's always a temperature set point. And the control variables are subject to some constraints. We have operating constraints and we have the service level constraints. Operating constraints, they are given by the technology, by the capabilities of the technology. So if you think about a heat pump, this typically has a startup temperature. So if the temperature, the outside temperature is too low, you can't power on your heat pump anymore. So this would be a minimum boundary. Then we have these service level constraints, which are usually more narrow than the operating constraints because they are based on the preferences of the users. So maybe your HVAC system can cool down your room to 10 degrees, or actually it would be fine with 10 degrees without consuming much energy. But then I think most residents would say that 10 degrees is not really what they feel comfortable with. So here we might have temperature bounds between, let's say, 18 and 28 degrees, something like that. This here is the same equation, just I reduced the complexity a bit, and here as a control variable we have it's called heat, so this is the temperature set point of the HVAC system now. And we have these constraints that I just talked about. Now, one complication in this equation is that in each interval, we change the set points. And this means that the ideal set point always depends on the set points that we use in the previous intervals. So we also have to take into account these previous set points and the external disturbances, like from the weather or sun coming in through the window, etc. And in order to do this, we use state space models. And here we found in experiments that this equation that you see on the screen now actually works quite well for predicting the room temperature. I really don't want to go into the details of this equation, but basically we have the state variable, which is the room temperature and the envelope temperature, like the walls, the floors, etc. We take into account disturbances, for example, from sun coming in through the windows and the outside temperature. And our control variable is the heating level. When we then plug in this equation into our model predictive control equation, then we are actually able to come up with these optimized power consumption profiles. But now it can actually happen that these power profiles that we identified as optimal don't really match what the trading manager had anticipated, and so it can't trade the flexibility that it promised to the energy markets, which is of course a problem. So to fix this issue, the trading manager now uses this power profile that it received from the flexibility manager and just repeats this calculation of the optimal internal prices, so that hopefully we now give the correct incentives for the buildings to adapt their power consumption. Then we send the new price profiles back to the flexibility manager. Flexibility manager again receives the intended consumption from the digital twins, sends it back to the trading manager, and then hopefully this matches the promised trading volume. If not, the process is again repeated until we actually achieve the conversions. Okay, this is actually the last slide now. I said before, it's really important for the project that we really implement the solution and test it in different demo sites. And these are demo sites that you can see here. We have 3 in Belgium, we have 1 in Barcelona, 2 in Poland, 1 in Germany, and 1 in Austria. And they are super diverse in the technology that they have, especially with regard to smartness. So we have some places where we can't control anything because we just don't get access to the equipment, even though some of our partners are the operators of these systems, but we just can't access it. So the only thing that we can do here is to send messages to the residents and tell them, hey, please set your AC system to, I don't know, 80 degrees now, and hope that they will comply. But this is something that will be really interesting for the social evaluations then. And then we also have demonstrator sites where we can control basically everything. And also where we have a lot of technologies. So sometimes we have local PVs. We have water tanks where we can store hot water. We have heat pumps, etc. So really a large variety of use cases, which would then hopefully allow us to get a comprehensive evaluation so that we know what actually works for other places as well. And that is actually the end of my talk now. Now I'm happy to take any questions that you have.
Yeah, so I hope I need the microphone. Thank you for the talk. Brings back some memories. We were working on similar topics. So I ask you the question I always get asked when I give talks like this. First one is synchronization effects. Right? If everybody's following the same signal, when the price goes down, everybody's incentivized to actually consume. And then the price goes up. So how do you deal with that?
That's why we have this iterative process. We anticipate that at the beginning it will not match, but then we have different price profiles. And this is also something we are skeptical about, whether it will really reach convergence or not. We just hope so, but we have to first do simulations and really test it in a real setting.
What is the time horizon you predict?
that depends on the market, on the energy market. So also depending on the demonstrator side, we want to participate in different markets, and then depending on their time horizon, that's our prediction.
Usually it's different markets, right? You have
Yes.
one market. And
Yes.
and the second thing is privacy. So the moment you do the digital twin, you're making a model of the building, which means you're making a model of the people inside the building. So how do you deal with that?
At the moment we don't. Well, of course, at our demonstrator side, the people know that this is a project and they have an incentive to participate. If you want to do this in other places, then also you have to get the consent of the people. I mean, you can't force people to participate in the programs.
What you're saying is that there's no way to avoid pricing.
No.
Yes. Thank you very much for your interesting talk. I have a similar question as before. I think you have in the market two different agents. On the one hand, you have some sellers. On the other hand, you have some buyers. As a buyer of an energy, you are interested in an almost low price, the lowest price possible. As a seller, you like to get typically a very high price. So at the end, someone has to decide what is the best price. And if I compare it to your optimization function, you have a minimization problem on the one hand for the buyer, maximum function for the seller, but who is doing the optimization of the system?
Yeah, there are two conflicting optimization problems. One maximization from the provider side and one minimization from the consumer side. How do you reconcile these two?
Well, we have to distinguish between the software of the project and the markets. So the markets, they are kind of separate. We trade in the markets, and then we get the price that is given by those grid operators. And then the minimization happens inside the Bluebird solution.
So you assume that the market price is given to
Yes,
the operators?
yes.
Who makes the software for the market system?
It's not a software. I mean, it's energy markets. It's just the
but it's
regular
not.
markets.
But it's not a natural thing like a stone or like a mountain. It's built by humans.
Of course, but I mean, they don't know about our
Americans.
internal workings.
Yeah. But who builds the software for the system?
It's a market. It's just a running market.
Yeah, but it's not a natural thing.
No, it's like a stock market. It's just bidding and prices. And
Casino, what you said before, it's once, well, as Bluebird will take over and govern all the homes, then it become a player large enough to have effects on the market. Then actually you're hitting the situation that you are actually depicting what Marco already hinted, that you have oscillation effects and all that stuff. But otherwise it's just two actors with opposite goals, obviously. Yeah.
I have a question myself. The trading manager, is it, so I guess it is distributed, right?
The trading manager? No.
No, it's single. It's a single.
Yes.
So is there, what is the slicing? So if it would be distributed, next project maybe, you are instantly I'm disappointed.
Do you know my view on European Union funds projects? But this is a different thing.
Okay, so if it would be, but still the question remains connected to Marco's question. How is the slicing mechanism of which consumers, which homes, for example, could be part of it? So maybe the effect that Marco is speaking about, maybe that can be somehow catered for when you slice it in a clever way that not all the same kind of profiles.
Or bigger, making a federation of...
Federation, you could even think of countrywide, statewide, whatever. You could slice it differently, maybe even different continents. Is that part of this project also, or is that the next project?
Let's say that it's not feasible with the demonstrator sites that we have, because I mean, you would need to consider like the whole country even to decide what the optimal slicings are. We only have
You have these sites.
singular sites, exactly, yeah.
Yeah, totally.
But it's a really interesting question, and I think that would be a good thing for the next project.
Fantastic.
So you mentioned that maybe this village manager cannot achieve what cost usually, so this is the penalty also savings costs based on so how do you attribute these costs or the savings to individual buildings?
Okay, only what? Can you repeat please?
So the overall focus
So maybe use the microphone.
Yeah. Wait, we have a second mic.
Okay, so the overall goal of the system is to save money or by distributing or by managing the demand of a building or of a group of buildings. So ideally, if the system works well, you save some money, or if it doesn't work well, you incur the penalty costs. Do you attribute these to the different buildings down to the flexibility manager, or is that not yet part of the system?
Well, I mean, we save money because we participate in these demand response programs, yes, and that's attributed to buildings, yes.
Okay, and the same for the penalties, then I assume. So if you would incur a penalty, that would also be passed on to the...
Yeah, I mean, that's kind of included then in the energy price, yes.
Okay, and is this then just based on consumption?
Yep.
Okay, thank you.
I mean, it's basically, you can compare it to just participating in a demand response program yourself. So the residents are really also the participants, just we have those mediators in between, because we don't have the volume as individual households.
And is the attribution, let's say, fair? So if 3 buildings participate, one cannot meet its flexibility and the other 2 meet their flexibility, is the penalty shared across all 3 buildings, or is it only for the building that fucked up, let's say?
Well, the thing is that we can't really say that someone didn't meet their flexibility or that they didn't meet their flexibility. They only have a certain amount of flexibility that they can provide, and then this is it. So in the end, it's shared across everyone equally.
Thank you.
More questions?
I really didn't get the overall goal. Is it to stabilize the market in the end?
Yes. Yes.
Okay.
So it's really the key is this flexibility so that we can contribute to the stability of the grid.
Okay.
Great. Thanks very much, Melanie, for your talk. Thank you. So as the first speaker had a no-show, we have an emergency speaker, a guest, Christian Becker. He will speak about from edge computing to edge AI. It's a tough topic. But I'm sure Christian will make it entertaining.
Das will ich so mit
Vorne auch, dass wir Kaffeepause machen, aber ich erzähle auch gerne was dabei. Es gibt nichts. Ja.
There's a break.